So, in our last lecture, our main focus was electrons, and then we looked at how they produce light. Since we're looking at light, it brings us, or rather it bridges us into what's called Beer's law, how the behavior of light through a solution can tell you items about the solution. Most importantly, we can figure out things about its concentration. So let me show you kind of what we're talking about here. Take a look at these two solutions. All right. You can see that there's obviously a physical difference between them. So let's go ahead and take a look at their behavior with light. All right. So we'll do the clear sample first and just take a look at what you see there. All right.
It's allowing the light to pass through.
So there's the lighter sample. And now we'll take a look at the darker sample.
That's how they made traffic lights.
All right. And you'll notice that the main difference between the two is that one is allowing more of the light to pass through than the other. And that's what we'll look at with Beer's law today, is what that tells us about the solution and what different items can change the intensity of the light to be altered as it travels through a solution. Bless you.
Oh, yeah, don't stack.
That was a cool trick. So, Beer's law is going to directly relate to the weakening of light as it passes through a solution and what that can tell us about the solution. There is a direct correlation between concentration and absorbance. Now, absorbance is a new word for you, and what it's going to refer to, and it's in an upcoming slide, is the amount of light that's not passing through the solution. All right? For example, if you think about the two that we had a moment ago, which one was absorbing more light?
The yellow one.
All right, yeah, this one here was absorbing more light. How did you know that? Well, because there was less light transmitting, is what I would say. Less light passing through is what that means. So the concentration is directly related to that then. So what we could assume is that the darker solution there is more highly concentrated, a higher molarity, than the lighter one, because there was more particles within it to absorb some of the intensity of light. So here's your two definitions. You're looking at transmittance versus absorbance, all right? And again, it's the cornerstone of the day, is understanding how these two words connect to each other. So said again simply, transmittance is simply the light that is allowed to pass through, whereas the absorption is the light that is, well, blocked. The light that doesn't get to make it out the other side as the intensity goes through the sample. Annalise, what are you doing? Okay.
Is Riddler part hard?
Guys, y'all are supposed to have the slides written. You're dividing.
I wrote periodic trends instead, all 16 pages. And I'm so mad.
So I'd like to make sure that we do have an understanding of what I'm talking about. So let's take a look at 3 beakers. All right, we're going to have 3 different beakers. I'm going to fill these 3 beakers. Actually, let's make him like this.
Beaker.
Now, I'm going to fill these 3 beakers with different solutions. All right? Or rather, different concentrations. So this one, we're going to say, is sitting at a concentration of 2 molar. This one, a concentration of 5 molar. And then this one, also a concentration of 5 molar. If the concentrations of beaker 2 and beaker 3 are the same, what does it look like I'm trying to show you is different?
The beaker.
What about it?
That there's more glass in the third beaker, so there's more light to travel through, like on the other side.
It's a thicker beaker. All right? Now, of course, to study Beer's law, we need to shine light through it. All right? So I'm going to take some intensities of light, and I'm going to make them all be equal to each other. All right? And I'm going to shine it through each of the beakers. Just like in the demo a moment ago, light will come out the other side. And I'm going to name these intensity 1, intensity 2, and intensity 3. Take a moment and reflect on what's up here. I would like to know the order in which the intensities decrease. If you had to compare these 3 values to each other and put them in order, which one would be the brightest, the most intense, and which one would be the dimmest? So take a moment and think about it. Jacob, which one would be the brightest?
Is it 1? Please tell me it's 1.
All right, his guess is that I1 would be the brightest. Which one, Isaac, do you think would be the second brightest?
I3.
He thinks I3. Do you agree?
No, I2.
I think it would be I2.
I was trying to go somewhere with it to see if I was.
All right. And then the darkest intensity would be I3. So let's talk about why. All right. The absorbance level is going to increase as the molarity increases. That's the whole point of what we're doing. So when we compare the first two together, the molarity difference is the direct reason why my second intensity is going to be less than my first. There's more particles in there. It can absorb more light, therefore a smaller transmittance. As absorbance goes up, transmittance will go down.
Okay.
All right? When I compare 2 to 3, the molarities are exactly the same, but the distance that the light is having to travel, we call it the path, is greater because we've got to get through all this extra glass. Because of that, we've got extra pathway, the same amount of solute, but greater than I1. Therefore, I3 would end up having the smallest intensity. Isaac, was there a question?
Yeah, so if I3 has more glass, right? That means that more glass is probably going to go, like, wouldn't more glass then go around the solution side?
So we are trying to ignore as much of the physics of this as we can, because you're talking about refraction and diffraction and stuff like that.
Okay.
We're not concerned about that. Remember, the only reason we're talking about this is we talked about how electrons create light when we talked on Thursday. And now we're talking about how that light, or light in general, can tell us information about what's inside the solution.
Is the glass absorbing as a light?
Yes, absolutely. All right, so with this in mind, let's put some of that into words. The first bullet there talks about the thickness, so you already have it in your notes. I do want to mention, and this is a loose definition. If I made 6 different molarities of sugar water, they would all look clear to you. So the color thing is not always super applicable, all right? But if you're asked a theoretical question, which in AP they'll throw that word in there to make it so that you're just answering like in the most ideal conditions. But if it gives you this sample, all right, immediately your mind should always associate the darker solution with the higher concentration. All right, that's what it wants you to do, even though all of the examples that you could run into in the lab might not reflect that. It's number 2. It's bullet number 2. So here's some of the variables that will refer to our transmittance and absorbance. However, these 2 equations right here will not be on the AP exam. They're not on your equation sheet, and they won't be on the test. I think the lab that I've written for you for this week will ask you a question that uses them, but the AP exam will not. Really, the biggest thing to take away from this slide is the 2 bottom bold. They're colorful online, but you've got to understand the inverse relationship between transmittance and absorbance, all right? Because if a lot of light's coming through, that's a lot of transmittance. That means that there's not very much being absorbed, and then vice versa is true. So if one goes up, the other goes down.
Did they get the name from looking at beer?
No, his name was Beer because he's a rock star. Yeah, but he had a yeast infection. So
Ew,
that was a beer joke.
Oh.
They make. Okay.
Is really hard.
So if those equations are not what we're using, we're going to inch towards the new equation that is on the AP sheet for Beer's Law. There he is. Now,
Yeah. No.
on your sheet, on the AP exam, it's actually going to be A equals ABC. Cool, right?
Yeah.
The way that it is on the slide is how I learned it in college. And I think it's still how you'll see it in college. So I don't really understand the A equals ABC, but that epsilon is a lowercase a on your sheet. The bottom of the screen says that. But here's how we can apply this absorbance transmittance concentration to draw conclusions about a solution that we're analyzing. So parts of the equation, first off, absorbance has no units. Sometimes they're called absorbance units, but in general, there's no units. That epsilon there is actually going to be a constant value. All right, the lowercase a is a solute dependent value. Depending on what you're dissolving in the solution that you're trying to find the concentration of, that number will be altered. All right. The B is the path length. Now again, in our picture, we know that the distance the light has to travel is a determiner of things. However, on the AP, this is a tripping point because the units will mess with you. B has to be in centimeters. They will give it to you in meters. So make sure you do the conversion before running the values. Isaac, put it away, please. Whether you're checked out or not doesn't mean you get to.
I was just playing 24
All the way away.
Oh.
Like invisible. And then finally, C is your concentration measured in moles per liters, of course. So before we get to our one real problem, because I don't think any of you will struggle much with this, I want to point out that while you won't be asked to graph it, you might be asked to analyze a graph of Beer's Law that puts absorbance versus concentration. Go ahead and go to the next slide so we can have values to look at. So we're not going to do it, but what we could do, this is an actual AP question that I just cut out of an exam. But what we could do instead of solving the problem is we could make a graph that puts absorbance versus concentration, all right? We could plot all of those points. And what will always be true about Beer's Law is it'll be linear, all right? So in our graph that you would have, it will be a linear line connecting all of those values. So once you have the line, you would know that everything that analyzes the solute that you're looking at, in this case it's potassium permanganate, but everything would fall on that line. So if you were given an absorption down here of 10 or whatever, and it wanted to know what's the concentration, well, you could just figure out where it hits the line and immediately know what the concentration of your solution is. Now, that is a less accurate way of solving. This is doing Beer's law without doing Beer's law, the A equals ABC. All right, but this will always be true about the data set associated with whatever solution is being analyzed. I care more about you being able to run the equation. It's on the AP sheet for a reason. So let's take a look at what they want us to do in the problem. So potassium permanganate, it gives you the absorbance that they're looking at, and they want to know the concentration. So it's kind of the exact thing I set up here. All right, they're giving one of the points on this axis, and they want to know where it will hit that straight line. They give you a wavelength, though, and here's another thing that you're going to want to make a note of. Wavelength does not have a place in Beer's law. It's important when running the data and getting your own stuff. You'll see during our lab on Wednesday and Thursday, when you use the machine to get your own data, you're going to get to pick any wavelength you want. And anytime you alter the wavelength, it alters all the other numbers. My point is that the wavelength value that you choose does not have a spot in Beer's law. I know that messes with you because y'all get all freaked out when there's too much information, right? There's a number there that you're not going to use, in other words. So the nanometers value for our Beer's law problems will not be applicable unless they're asking a larger problem that then they want to know things about wavelength. But Beer's law itself doesn't use wavelength when running or trying to find a concentration. So, what is the steps in actually solving this problem using Beer's law? Well, the way that they give this information and the way that they will on the AP exam is actually going to set you up to use Beer's law twice. What we're going to do is we've got a bunch of published data that we know is true about potassium permanganate at that wavelength, all right? So what we can do is use that data, find information, the missing information that correlates to the experiment they did, and then run it again. So let me show you. We're going to be using A equals ABC. The information that they don't have in their experiment is the molar absorptivity, right? They don't know that lowercase a, all right? So what we can do is using the published data, we have everything we need to find it. So what I'm going to do is pick one of the data sets from the bottom, all right? I'll just pick the top one because why not? So I'm going to pick the very top data set, and we can plug into this equation to solve for lowercase a. So the absorbance there is 0.162. All right, we're going to find our constant here. Hey, what does B stand for? The path length, right? Look at the problem. What is the path length in this problem?
540.
It's 1 centimeter. Do we like those units for B?
No. Yes, because it's centimeters.
We do. Yeah, so it's 1.0. So we can use that as is. And then what's the concentration of our data set?
0.0300.
How did what? Because the path length is the amount of distance that the light's going to have to travel. And this solution exists in a 1 centimeter cell.
Are we saying path length or path length?
Length.
It's like where you got the 3 why?
Because we can run any of these data sets, because we're looking for a constant value that can apply to anything on our linear line, all right? And this data set is what builds the linear line. So what we're doing is we've realized that we have everything we need to solve for that constant value. if we use one of the established data sets.
So we just have to make sure that we could have used any of them.
You could have used any of them. You'll end up with the same thing. So what I'm going to do then is solve. Some of you might have already solved. All right, but if we solve for our molar absorptivity here, I'm going to end up with a value of 5.4.
That's what I thought in my head. You
It's all from the first. I just chose the first data set. If you look at the first data set, 2 of my 3 numbers comes from it. So check out what I know now. I don't have an answer to their problem. They want to know the concentration of their sample. Well, their sample doesn't fall into the published information, right? They don't. They're wondering. All right, they know kind of where it falls in between the published info, but they're running an absorbance of 0.539. So now what we can do is we can go Beer's law again and solve for concentration, because that's what they want to know. How concentrated is their sample of potassium permanganate? So we've got all these values now, but now we're going to go to their experiment. Their absorption, they said, was 0.539. Our constant value is 5.4. We just figured that out. They're using the same cell, which is important because you want the experiment that they're doing to match the data that we ran, that we got our constant from. So it's still 1. But now we can find the concentration of their data. Yes?
Is the 540 the number we're not using? That's the wavelength?
Right, that's the wavelength that they set the machine on to collect all of the data.
Where's the 540 at?
It's the wavelength that they use to collect the data in the spectrometer.
It's just us. It's just been converted, right?
It hasn't. We haven't done anything with it. It's got no place in Beer's law. But if you were going to repeat this data, you'd have to set the machine to 540. Otherwise, you would get different numbers.
How many sig figs is it?
Looks like 2 to me. And now we can get an answer to their problem, which could be incredibly useful for us if we knew we had an unknown solution of hydrochloric acid or whatever. We didn't know what the molarity was. We could use this light technique to actually figure it out.
It's like 1.0.
Anybody want to put an answer in? Yeah, 0.10.
Wait,
what?
why?
I got 0.09. Yeah, but you have to round it.
Well, you can only have 2 sig figs, though. It should bump itself up. I mean, if you got that, what did y'all get? 0.0998?
Yeah.
You did it right. Now you just have to know how to round.
Oh. Now you just need to know how to do your job.
I just never know
Now you.
Well, there's 3 and 2 and 2, so
you know
2
how to do
wins.
your job.
I know, but I always have like constants. Like,
That's how?
Yeah, but none of these values were constant. This could all be manipulated. The problems that AP will ask you using Beer's law are, first off, they're about every 3 or 4 years. They don't use the equation very much. They actually ask more. There will be Beer's law concepts on there, absorption versus transmittance, but this question's not always there. But if it is, it looks almost exactly like this. So, hey, I've got good news. There's one more slide now. Dang it, I didn't print it for y'all though. Oh yeah, there is.
I have a theory. Is Rylan part Harl?
Is what?
Rylan part Harl?
His name is Rylan, and you'll come up with all your own conclusions about his. I'm sorry, I forgot I didn't print her a copy, so I'm going to pull up the slide so I can copy it off. You'll notice that we have a larger chunk of time than you're used to having.
Wait a minute. We're done?
No, there's one. We're going to do one more problem together. But let me pull it up.
Oh Okay, what flavors you got?
Yeah, it's not even on the slides.
Only Carol was
Flavors you got?
Do what?
It's not on the slides.
I know it's not. I told y'all it is an extra slide.
extra.
Hey, that's it.
Yeah.
All right, I can't pull it up, but I think I have enough information here.
Okay, go.
All right, so write this down.
Because you were doing so much before.
I want to know who has smaller transmittance. All right?
So this isn't like a learning new stuff.
No, this is practice on what we just did.
Yeah, this is serious.
Who has smaller transmittance? I'm going to give you sample A is one of your choices. And sample A is going to be 1.5 moles of lithium salicide. And that's going to be in 822 milliliters. That's one of our choices. And then we have sample B, who I'm going to say is 83 grams of beryllium borate. And he's going to be in 0.35 liters. So you've got two samples here. I want to know who's got smaller transmittance. See how far you can get in this problem.
Beryllium.
You should be thinking molarity. Talk to a neighbor if you get stuck anywhere. No.
Sabrina, can I have a sausage?
You're already on chapter 41. Book two?
Yeah.
Here.
At the beginning of the book, there was a part where it said begin flashback and then present day. Was that mentioned in here, or was that just left over back?
I have an editor.
Okay. There was also a part where it was a period and then it just started.
Hey, you're working. You're working.
I'm gonna.
Don't be distracting if you're not working.
I stand by my theory that real life is part of it.
I think these are asking me with salsa.
Go to best practice.
It looks like breakfast.
That's the way you would practice.
Like Mexican breakfast.
You walk up to his wife and say, you walk up to his wife and say,
Remember, the transmittance and absorbance can directly be concluded from concentration. You're not using A equals ABC here. Sorry. Oh.
It's okay, man. I'm not waiting. Want them? No. Here you go. Yeah. Area food. It's like they put like chorizo and egg tacos like in a bowl, just mashed.
Where's West at right now?
West.
Where's the salsa in that?
Oh, where's Companion right now?
Companion?
Hey, Matt's cow disease? It tastes like a chorizo egg and cheese taco.
Can't get a diet.
When's the last time you saw Companion?
Soft and
It
tender.
was like 2 seconds ago. He was finding them and then he was, oh, wait.
I like the vanilla.
You gotta get it in the paperback.
Look, we are trying to game.
I see. They just did the logic.
Alright, so you're right, so companions, they're just returning the striker.
Okay.
You want
These
some?
names are very peculiar. Did you make the 9? There's 5 realms, right? Was that based off of the 9 realms?
No, they're 9 realms.
There's 9 realms. Is that based off of the same 9 realms? That's like in total?
No, man, this is not a rollover from.
I don't know. It seemed very similar. There is realms and then there's.
I started writing this before there was Marvel movies.
Well, I mean, Marvel movies is still Marvel. The comic books. There's gonna be like different multiverses.
Oh.
Uh-oh.
Somebody drew on one of your erasers.
I started reading it and I was like, I recognize this. I know this formula. I watched many things I haven't seen formula. Read
So you know what's going to happen? Are you telling me?
Actually, I predicted a lot of the deaths.
Oh my
I was
god!
like, Karamir's gonna die. I could tell. Then he died. I was like,
So means
my
the
next
violate
predicted death is
the
Leaks, the dog. Am I right?
I can't tell you.
What the heck?
After I work this out, you know you're not interested in watching the answer? All right, let's take a look. All right. So we know that in general we can compare molarities to draw conclusions about absorbance and transmittance. So we need molarities. Looking at A, all right, well, first off, we know that molarity is moles over liters. All right. So that's the equation that we're using. So here I would take, hey, look, I'm given moles for A. All right. And I need to divide it by liters. So what are we going to divide it by?
0.822.
0.822. All right? And I immediately will get a molarity of A, and I get 1.82 molar. All right? And that is sample A. All right, well, B requires more work. So for us to do B, it gives us grams, and that's not okay. So we need to go to moles, but we know how to do that. So I can go my 83 grams, all right? And we need to go to grams of beryllium borate. I hope you built it correctly, because it's BE3,
Oh.
BO32 is beryllium borate. Anybody have his molar mass? Perfect, 145.65.
For 1 mole of beryllium borate.
All right. So if we run our grid there, we'll end up with what looks like 0.574. All right. And that is moles. Of course, we want to go moles over liters, but look, it gave us liters this time, so we can just use 0.35.
Dang, I was correct.
I'm sorry? 83 times 1 divided by 145.65. You got what? Did other people get this number?
Yes, but I'm just saying it's 144.65. That matters.
Oh, it's 144. Oh yeah, that's what I got. All right, divided by liters. So when I run that there, it's going to give me my other molarity, and in this case, that's 1.64 molar. 1.64 molar. That's B. So the question is, and now here's where you've got to show that you know what you're talking about. All right, it's spiraled in a molarity calculation. It's going to do that a lot. All right. Now, do you know the science? Which one has the smaller transmittance? A.
Because it's big.
Because a higher molarity will have a higher absorbance. more particles to take it to block the light. A higher absorbance will always have a smaller transmittance. You what?
I'm smitten. I hate the hell out of this. What?